afternoon. It is afternoon. No, it's actually still morning. Welcome to Coronachem Day 41 for grade 12, period 4, Tuesday, June the 2nd of 2020. This is your homework from yesterday. You were asked to do the practice example from page 641. It says, given that at 700 Kelvin, Kp equals 54 for the reaction of hydrogen gas plus iodine gas to give you 2 hydrogen iodide gas, and that Kp equals 1.04 times 10 to the minus 4 for the reaction of nitrogen gas plus 3 hydrogen gas to give 2 ammonia gas. Determine the value of Kp for the reaction of 2 ammonia plus 3 iodine gas gives you 6 hydrogen iodide plus nitrogen gas at 700 Kelvin. So here are the 2 reactions that you're working with. This is your target reaction. They've given you the Kp values for the 2 starting reactions, and they want you to somehow combine these 2 reactions to produce that reaction. So we start by flipping reaction number 2. We write it backwards so that you get the 2 ammonias that you need, and then all the other things up here on the other side. So when you flip a reaction, you take the reciprocal of the Kp. So the reciprocal of the Kp is 1 over 1.04 times 10 to the minus 4. You get this number. Then to get I needed 3 iodines, and I only have 1 iodine in the first reaction. So if I multiply that first reaction by 3, I get the 3 iodines I need. The other stuff takes care of itself. So I multiply reaction number 1 by 3. When you multiply a reaction, you raise its Kp value to the power of 3. So 54 to the power of 3 gives you that number. Now you add these 2 reactions the same way you would with Hess's law in chapter 5, and you get your target reaction. When you add 2 reactions, the result is that you multiply the values of Kp. So I multiply the 2 results I got, and the final answer is 1.51 times 10 to the power positive 9 for this particular reaction. Up to now we've been doing reactions where everything is in the same phase. That's called a homogeneous equilibrium. Equilibrium if it's one reaction. If it's multiple ones, then you have equilibria. So in homogeneous equilibria, all the substances involved are in the same phase. In heterogeneous equilibria, not all substances are in the same phase. So for example, if you have a solid substance immersed in an aqueous solution, that's a heterogeneous equilibrium. Typically, I won't say typical, I'll say always, whenever you have heterogeneous equilibrium, you do not include the solid into the calculations of the equilibrium. You only include the things that are in the same phase. So all the if it's all gas phase, then you include gases only. If it's all aqueous phase, you only include the aqueous. You don't include a solid in an aqueous equilibrium. So the next example is where we're going to calculate the equilibrium constant for a heterogeneous equilibrium. So this is on page 641. It's a note, an example of a heterogeneous equilibrium. So for example, you have lead chloride, which is a solid, producing plumbous ions in aqueous solution plus 2 chloride ions. It's a heterogeneous equilibrium. The concentration of pure solids and liquids are not included in the equilibrium constant expression. So Kc will be equal to the concentration of plumbous ions times the concentration of chloride ions to the power of 2. The use of ice tables allows the easy tabulation of initial and final values in order to calculate the concentrations of other substances in the reaction. We're going to use an example of that on page 645. You're familiar with ice tables. I've given you many examples of them. On page, I skipped over one example. On page 642, it asks you to write the following equilibrium constant expressions, and they have heterogeneous equilibria. So you only include the parts that are AQ. For example, in part A, it says Kc for chromium solid plus 3 silver aqueous turning into chromium aqueous plus 3 Ag solid. You'll see that the chromium aqueous is included in the numerator, products over reactants always, and in the denominator you include the Ag to the power of 3, Ag plus to the power of 3. You don't include the solids. And in example B, you have gaseous reactants, so it's H2 to the pressure of H2 to the power of 4, because the stoichiometric coefficient of the hydrogen is 4, and also the water coefficient is to the power of 4. You do not include the solids. You'll see that on the top of page 643. And the next example that we want to do is on page 645, where we're going to calculate an equilibrium constant. On page 644 they give you a homogeneous one. Well, let's do the homogeneous one first. It's the easy one. So practice example on page 644. They tell you that an aqueous solution of acetic acid is found to have the following equilibrium concentration at 25 degrees Celsius. It gives you all the concentrations. I'll show you what the reaction looks like. So acetic acid is CH3COOH. I know the book spells it, does it in a slightly different way. That's the way I'm used to it. It's more recognizable. The molecular structure is more easily recognizable to me in this form, but it's the same molecule. I'm just portraying it in a slightly different way. This is what you get when acetic acid dissociates. They're telling you the concentrations are 1.65 times 10 to the minus 2 molar. The acetate anion is 5.44 times 10 to the minus 4. And the H plus concentration is also 5.44 times 10 to the minus 4. This is easy stuff because you've already done the acid-base unit, so you know all about ice tables. So the Kc in this case is going to be the concentration of the acetate anion times the H plus ion over acetic acid concentration. So you're going to get 5.44 times 10 to the negative 4 squared, because it's the same number twice, over 1.65 times 10 to the minus 2. What you get is Kc equals 1.79 times 10 to the negative 5. The next one is a practice exercise, and it's the practice example on page 645. The question reads, sulfur trioxide decomposes at high temperature in a sealed container. It gives you the equation. Initially, the vessel is charged at 1000 Kelvin with SO3 gas at a partial pressure of 0.5 atmospheres. At equilibrium, the sulfur trioxide partial pressure is 0.2 atmospheres. Calculate the value of Kp at 1000 Kelvin. So here's the equation. 2SO3 gas is forming sulfur dioxide gas plus oxygen gas and you got 0.5 and then 0 initially, and then at equilibrium they say that you have 0.2. So that gives you plenty of information. So you have the stoichiometry of the reaction. Because you've gone from 0.5 to 0.2, it means it changed by 0.3. So you have minus 0.3, which allows you to reconstruct what happened over here. If you lost 0.3 over here, it means you gained 0.3 over here. So this is going to be plus 0.3. And at equilibrium it's going to be 0.3. This is going to be half as much because the stoichiometry is 2 to 1. So this is going to be plus 0.15. And it's going to be at equilibrium at 0.15. So that way you can reconstruct all the concentrations at equilibrium. The Kp expression is, again, products over reactants. Remember that the coefficients become power, so the sulfur dioxide concentration is squared times the oxygen concentration over sulfur trioxide concentration squared, and then just plug in all the numbers. If I sound a little bit winded, it's because I gave blood yesterday, so I actually feel a little bit out of breath writing on the board, believe it or not. But it takes a couple days for my body to make new blood, and then I feel all better. Here are the numbers once you plug them in, and you get 0.3375. And then you're only allowed 3 sig figs, so it ends up being 0.338. Now you get a quantity called the reaction quotient, where you can determine which way the reaction is going to head based on the initial concentration. So the reaction is not at equilibrium yet, but by plugging in the numbers, you can do a calculation, then you compare it to the actual numbers that you should have at equilibrium, and from that you can predict which way the reaction is going to go. That's called the reaction quotient. Reaction quotient. And they use Q as the symbol for it. It's a number obtained by substituting starting reactant and product concentrations or partial pressures into an equilibrium constant. Continue at the top. So I'm looping back over here. Pretend I'm going to a second board. The resulting value allows one to make predictions about how the reaction will proceed. So, if Q equals K, it's at equilibrium. If Q is bigger than K, it moves left. If Q is smaller than K, it moves right towards products. So example, practice example, page 646 and 7, loops over to the other bit, wraps around to the next page.
It says at 448 degrees Celsius. Oh no, sorry, that's the actual example. The practice exercise. It says. Just making sure I'm in the right one. Yeah, at 1,000 Kelvin, the value of Kp for the reaction 2SO3 gas gives you 2SO2 gas plus O2. So the same reaction as the last one we did. calculate the value for QP and predict the direction in which the reaction will proceed toward equilibrium if the initial partial pressures are PSO3 is equal to 0.16, PSO2 equals 0.14, and PO2 equals 2.5.
So you get 2 SO3 gas, 2 SO2 gas, and O2 gas. Kp of the reaction is 0.338. We determined that in the last. So we're determining the value of Q. We get 16.4, which is bigger than K. So K is 0.338. We're getting 16.4. Because it's bigger than K, the reaction is going to move left. It's already gone past equilibrium, so it's going to move back. It's product rich. The reaction is product rich and will move left.
Okay, so I'll give you for homework, practice example 648. So read through that example. It asks you to calculate the final concentrations. On this one, you're going to need to use, practice example 648 is easy. If you're feeling particularly daring, try 649 as well. Okay, so that's your homework. Homework, practice examples 648 and 649. This one's going to require a quadratic formula. If you think you can do it, press me. I'll give you the answers tomorrow. Okay? Also, I've made the answer keys for the tests that you handed in yesterday at 6 p.m. So I'll be, tomorrow, if everything works out, I will give you the answer key. I'll go through the test questions. We'll answer them together for the kinetics test. And I will hopefully have a mark for you sometime by the end of the week. Okay, so we'll see you tomorrow.